Welcome, everyone. Thank you for joining Lesson Learned on Running Hadoop on Kubernetes session. My name is Chen Qiang. I'm part of data SRE team at LinkedIn. Our team manages entire offline data infrastructure, including Hadoop, Spark, Presto, and many others. Kubernetes at LinkedIn started about a year ago. Our team was one of the first users, and our main use case is to launch ephemeral Hadoop cluster for development and testing purposes. There are many lessons learned from our journey, and would like to share some of the challenges, problems we encountered, as well as solutions in order to successfully running Hadoop on Kubernetes with overlay network. In this session, I will cover Hadoop basics for audiences who are not familiar with Hadoop and briefly touching on Hadoop footprint at LinkedIn. I will talk about the initiatives for this project, architecture overview, and the challenges walkthrough. In addition, I would like to share the insights of what currently we are working on and a future roadmap. At the end, it will be a 10-minute video, including spinning up a secure Hadoop cluster on Kubernetes, doing some file operation, running a Hadoop job, as well as in-place expansion. Let's start. What is Hadoop? Hadoop is a collection of open source software designed to handle big data storage and computation. The main components of Hadoop are Hadoop Distributed File System, HDFS, which is a POSIX-like file system and designed for distributed computing framework, and it is highly reliable and resilient. HDFS has three types of components: a HA pair of name nodes, which holds metadata of entire file system; quorum of journal nodes saves the incremental metadata for later compaction; and many data nodes that store the actual data. Above HDFS, there's a Yarn. It manages all distributed compute resources, including CPU, memory, and GPU across many worker nodes. Yarn has four types of components. Resources Manager manages hardware resources, schedules workflows, and monitors jobs. History Server archives completed jobs, and a proxy server redirects users' requests to either Resources Manager or History Server, depends on the job state. Last is a Node Manager. That is the one actually runs the task. On top of those, there are many distributed computing frameworks such as MapReduce, Spark, Presto, and many others. Last, but not the least, is the client, such as Gateway for CLI, and many other open source schedulers, such as Azkaban, Apache Uzi, and Airflow. Hadoop at LinkedIn. LinkedIn is a large Hadoop shop, and we have been continuously investing in Hadoop for past 10 years. We are running one of the largest Hadoop environment in industry. We have more than 10 Hadoop clusters, and all of them are running on bare metals. Our largest Hadoop cluster is over 7,000 physical servers with storage capacity of 400 petabyte, 500,000 CPU vCores, and 1.6 petabyte of memory. And we are constantly pushing the limit by adding more nodes. We have multiple super large clusters with over 4,000 nodes each. We serve thousands of users across entire company. Our average HDFS read and write throughput are over 600 gigabytes per second, respectively. And every day, we have over 300,000 jobs with 100 millions of containers running. Our HDFS is very well tuned and can easily handle more than 100,000 QPS. Our team also manages LDAP, Kerbals, and DNS infrastructures to support secure Hadoop clusters. Our average LDAP, KDC, and DNS QPS are 150,000, 5,000, and 95,000. Our Hadoop environment generates huge network traffic with average bandwidth of 15 terabits per second. So as I mentioned, LinkedIn has a large in-house Hadoop development and SRE teams that are constantly working with open source community, contributing features and bug fixes. Having Hadoop ephemeral cluster running on Kubernetes allow every engineer to have own cluster for testing and development. In addition, the cluster is running with immutable container images, so the issue is always reproducible. This approach significantly boosts the productivity and efficiency with only 3 minutes to spin up a secure Hadoop cluster comparing to hours or days building a testing environment on the bare metal. Let's have a quick architecture review. It builds on top of Kubernetes overlay network. Each component requires a Kubernetes service to have a static and a DNS resolvable hostname for communication between pods, as well as service discovery. For every admin nodes, such as journal node, name node, resources manager, there is a service associated with that with one-to-one mapping. For worker nodes, which is a data node and a node manager, it is N-to-1 mapping. All data node or node managers shares the same service. So the graph here shows all the communication paths in between, and all the connections are through service endpoint. Let's move to the challenges. Over the course of the project, we encountered many challenges, and I would like to share some highlights with everyone here. First one is DNS. It took us days to find out a good solution without compromising security. Next is network. By default, there is no fixed or predetermined hostname in pods or deployments with overlay network. Hadoop admin nodes requires those fixed hostname to be listed in the Hadoop configuration before the deployment. Third is the identity. In secure Hadoop, every pod requires a unique Kerberos credential for authentication. Due to the unknown of IP addresses or hostname at launch time, we are not able to pre-generate those. Last but not the least is the orchestration, because there are strong dependencies between Hadoop components. For example, HDFS name node must start after all the journal nodes are up and running. Now, I'm going to walk you through every problem in detail with solution. First one is the DNS. Hadoop worker nodes, which is a Yarn node manager or HDFS data node, talks with each other using host names. By default, there's no global resolvable hostname associated with it. Also, it is impossible to have one service per work pod because it won't scale natively with Kubernetes. Second is insecure Hadoop authentication also require IP reverse lookup matching nodes Kerberos principle. For example, yarn/_host. The underscore host will be replaced by the hostname in the Hadoop logic with hostname-f, and a mismatch will obviously result authentication failure. Next is the web HDFS, which is a REST API endpoint for HDFS. When name node sends the redirect request back to the client, it contains a host name of designated data node that going to be serving the actual request. And the last is for MapReduce or Spark jobs. Application master and the Spark driver are sharing their host names with the workers. So the solution here is, by default, the pod does not provide a global DNS resolvable hostname. The solution is to using stateful set with headless service. So it will provide every pod with a global resolvable hostname. Unfortunately, it does not solve the problem. We found the hostname resolution and the reverse lookup was inconsistent, as you can see my example here. So when I do the hostname-f, it come up with the hostname with pod name. However, when I do a DNS resolution on that, it shows up as a unknown record. Then I do a reverse lookup of the pod IP addresses. I get a actual DNS resolvable hostname. So the solution here is we injecting the actual DNS resolvable hostname to the pod's etc hosts file at startup time. Then it resolves all the DNS issues we have to running actual workload on Hadoop. As you can see, I get another example here underneath it is after we injecting the actual resolvable hostname into etc hosts file, then all the forward and reverse lookup are matching. Next one is the network. There are many components in Hadoop, and they are communicating with each other while the cluster is up and running. Like, for example, data nodes initiate the connection to the name node. Node manager initiates the talk to the resources manager. And there are many intercommunication between components as well. And Hadoop configuration must be pre-populated with those host names of admin nodes in place before we start the service. The solution is to creating a Kubernetes service for every Hadoop admin pods. It provides a DNS resolvable and a structured hostname, which can be defined and populated in Hadoop configuration before the actual deployment. So I include a snippet of configuration XML for Hadoop name node. So as you can see here is we have name node HA1 and HA2, and each of them using the service endpoint. Next one is identity. It only applies to the secure Hadoop cluster with Kerberos enabled. Every Hadoop component requires a Keytab file with a service principal. For example, HDFS/DNS resolvable hostname at your Kerberos realm. The hostname has IP addresses embedded, and it is impossible to pre-generate them and pushing in the pod. Our solution is to introduce a Keytab Delivery service running in Kubernetes. It authenticates the request from Hadoop pods, generating a QA-only Keytab and a send back to the client. In Hadoop pod, we have an init container to reconstruct the hostname by replacing the _IP with the actual DNS resolvable hostname and send the request to the Keytab Delivery service. Unfortunately, we don't have much time to go through the authentication workflow, but luckily it uses the same authentication mechanism at LinkedIn recently open source project Kube2 Hadoop, and now it is available on GitHub. Please feel free reaching out to me if you would like to know more. Orchestration. Last is the orchestration. As I mentioned, Hadoop components have hard dependencies in between. For example, name node must start after general nodes are up. The obvious solution is to launching general node pod first, then name node pods next. Such approach usually results long deployment time and a complicated external logic to orchestrate deployment sequence. What we come up with is introducing a init container to constantly polling status of depending service using service discovery with pod env. Init container would exist successfully when the depending service is up, and the main container can proceed. With this implementation, we are able to launching all pods simultaneously and reduce cluster deployment time down to 2 to 3 minutes. I include an example of init container here that polling the status of HDFS journal node. So that is the end of our challenges. And what is the next? So it is a great lesson we learned to having Hadoop running on Kubernetes as testing and sandbox environment. We are almost done to have other big data components such as Spark, Presto, Azkaban, Hive as part of our ephemeral Hadoop cluster. In meanwhile, we are also working on long-running Hadoop cluster on Kubernetes to replace integration environment that is currently running on bare metals. And the number of issues we've encountered are not less, but we do see 20 times faster deployment speed. Our next major goal will be Kubernetes custom resources definition and Hadoop operator. Hopefully we can open source those when they are ready. The key takeaway for this presentation will be it opens the opportunity to combine different workload onto the same resources management platform. I know a lot of company has separate infrastructure serving online and offline, and the online infrastructure usually idle or less load during off-peak hours. Leveraging those idling resources will easily save company millions of hardware cost. Second, it may change the way how the big data infrastructure are running. A lot of Hadoop native distributed framework are now running natively on Kubernetes. For example, Spark and a LinkedIn open sourced SAMSA. And the last, and make Hadoop to Kubernetes transition much easier, which kind of resonate the very first point. That is the end of the presentation. By the way, there is another session tomorrow presented by my colleagues, Abin and Frank, talking about petabyte scale AI at LinkedIn. So let's jump into the demo session. Thank you. A short video to demonstrate bootstrapping a brand new ephemeral Hadoop cluster, including HDFS and Yarn on Kubernetes with overlay network. Let's deploy a cluster now. Cluster name is KubeCon 2020 demo deploy. This is a wrapper and it does three things. First, it uses Python Jinja to templating engine to render many YAML files, including pod, service, stateful set, definitions, and config maps. Second, it does YAML file validation by YAML linked. And last is to apply those YAML files onto Kubernetes with a specific order. It starts with service, then config map, and the last pod stateful set. Each pod has at least one init container to fetch Kerber's Keytab. And some pods have one additional init container for dependency check. For example, in HDFS, the name node should start after 3 journal nodes are up and running. I have successfully applied all the YAML files. Let's check in the pod. Let's check the config map. And let's check the service. They're all newly created. Let's back to the pod again. Just under 110 seconds, we have 15 pods up and running. Among those 15 pods, 8 of them for HDFS and 6 of them for Yarn. HDFS including 3 journal nodes, 2 name nodes, and 3 workers. Yarn has 1 resources manager, 1 proxy server, 1 history server, along with 3 node managers. We have one more pod, which is the gateway. We are using that to interact with our cluster. Let's check our web UI. Here is the job history web UI. So it archived all the completed jobs. The resources manager web UI, and we have 3 active nodes. And here is our name node 2 and name node 1, and they are 1 active and 1 standby. As I mentioned, we have 2 name nodes here for high availability. One is active and the other is standby. We are able to fail over between them, and all the client will automatically connect to the active name node for HDFS transaction. During our startup process, we have failover testing to making sure that it works. Now we have our Hadoop cluster running. Let's interact with the cluster using our gateway pod. myself. So I'm accessing my home directory on HDFS. And I got GSS initiate failed because we are running secure Hadoop cluster and we require a valid Kerberos TGT. So once I have a valid TGT, I'm able to browse my file system. So right now I don't have any files in my home directories. Let's touch a file. So I create a new text file called kubecon 2020-demo.txt. Let's uploading this file to my home directory in HDFS. Let's do a list again. As you can see, my file has been successfully uploaded to HDFS. Now let's submitting a job. It is a very simple pi calculation job. Usually this job should take no more than 30 seconds. As you can see, we have successfully submitting the job to our resources manager. Let's go to the resource manager page and refresh here. As you can see, my job, here's my job ID, my username, job name, start time, launch time, and the state is running. And the std out from the job submission is constantly getting updated with the status. And here you go, the job finished just under 27.5 seconds. Let's refresh the page again. As you can see, our job now is in finished state. Let's go to the job history server. So because this job is a completed job, that's why it's showing up in our job history server. In job history server, I can dig into more details with the job. Like for example, I can see the log for each running task. Right here, then I can go logs. That's all the logs here. Okay. The cluster initially started with 3 workers, and in some use cases, it required more resources to run large workload. Since worker nodes are defined as stateful set, we can easily expanding them. kubectl scale replicas equals to 10 stateful set kubecon 2020 demo. So we are expanding our HDFS data node from 3 pods to 10 pods. We are doing the same for the Yarn node manager. Let's check in the pod. Data nodes and node managers are spawned in Kubernetes cluster, and they will join automatically to Yarn and HDFS in next 30 seconds. Under 30 seconds, we have the additional data nodes up and running, and as well as the additional node managers up and running. Let's go back to the web UI to see whether those nodes are joined our cluster. To refresh the page. Okay, so active nodes from 3 to 10. Check the HDFS. It also increased from 3 to 10 nodes. Usually when we're doing expansion in our data center with with the bare metal setup, it usually takes about hours to expand. In here, we are talking about 30 seconds. Okay. After the testing is done, cluster can be easily torn down. It deletes all the pod stateful set config map and services. In next minute or two, all the pod will be terminated. This concludes the video. If you have any questions, please join the question session and I'm more than happy to answer. Thank you.